I got sick this week, so I didn't prepare a very long presentation. So the idea is just show some ideas here and maybe do some computations in the whiteboard. So the idea of this discussion is to talk about the likelihoods, right? Because we know that I use there a pointer here? No. Okay.
I should use this one.
No, yeah, it's not very important.
No, it is important. I need to see. I mean,
Okay, so okay.
Just hold the button.
I see. Thank you. So okay, for any inference that we do in physics, in the end of the day, we're actually trying to find this guy here. Sorry, this guy here, which is the posterior distribution function of some set of parameters of your model, given that you have some set of observations and of course some model. Okay, so this is always the main guy in any Bayesian analysis. Okay, I suppose that for particle physics, Bayesian analysis is not very relevant, but for cosmology, it's the only way of doing things, right? Because you have only one universe. So to compute this posterior distribution, which is basically the distribution of your parameters, you need to know your prior. Your prior is just the same thing of the posterior, but inverted here, right? So it gives you the probability of seeing some set of data given some set of parameters and a model. Okay. So the point of this stuff is just to discuss about this guy here, the likelihood, and how to get this likelihood for some particular activity. So first of all, let's talk about the usual way of getting the likelihood. The usual way is to assume the central limit theorem. So the likelihood is simply a Gaussian with where you have here your observational data, your theoretical prediction for the same data, and your prediction for the covariance of this data here, right? In principle, both the prediction for the 1 point and 2 point momentums here, you can compute directly from the theory or from any of our simulators, right? But the whole point here is that you have a really huge assumption here, which is the functional shape of this distribution here. You are basically fixing all moments of this distribution with n larger than 2 to 0. So you are putting a very strong prior in your model, right? That you have no reason to do. Your only reason is the, again, the Gaussian limit theorem. So I'm going to talk about two main strategies to try to find this likelihood, the true likelihood. One is a completely theoretical approach, and the second one is a completely numerical approach. So here there needs to be the two flavors to you.
So you want to get rid of the three assumptions or anything?
Just the third one.
Just the two.
The first one.
The first one.
Yeah.
So
we are going to see that if you really try to find the likelihood, you are automatically finding the prediction and the covariance. So we are actually really getting rid of the 3 points here, but only trying to get rid of the third one. Okay. So we have here just two possibilities. One is that you have a good theoretical model, and the other one is that you have a good simulator. Okay, and in both cases you are able to recover the likelihood under some simplification, of course. So let's start with the theoretical model. So here we are going to suppose that we have some observation. In this case, I am using the density field of some tracer. Okay, so I have a collection of tracers in the universe, like galaxies, halos, or anything else, gravitational waves, or anything else. and you put these points in a grid, so you have a proxy for the density field of this tracer. And the density field of this tracer, you can, for example, expand in terms of the primordial potential, which is the only object in the universe. Okay, but remember that if you assume that all initial conditions are the same, which is what's the name? The name? And you assume that
They are all the same.
yes, forgot the name. There's a name.
Scaling line and close, but
No. For that you don't have, for example, isochronometric perturbations or
Adiabatic.
adiabatic, yes. You assume adiabatic initial conditions, so all initial conditions are the same. So the only degree of freedom that you have is the initial gravitational potential that's given by the Newton. But yeah, once that.
So is there a motivation to work in Fourier space at this point?
No, just simpler. Yeah, I think nothing's back
Because simulations are in real space. That you're going to do.
No, right? You use both space usually, right? The mesh part is usually in Fourier space, actually. So you combine both. The Fourier space is more useful usually because you are working with a really large range of scales, right? In real space, really hard to do that. So in Fourier space, is much simpler. And so we have the initial gravitational potential here, which is represented in terms of the initial density field, which is just Laplacian of this gravitational potential. And here we have a stochastic field. This stochastic field has basically the information of how the small scales affect the large scales. That's the meaning of the stochastic field. Okay, we always use in cosmology. So how the physics above your cutoff scale is lambda, will affect the physics. Yeah, the physics in energies larger than lambda will affect the physics in energies smaller than lambda. Energy smaller than lambda means scales larger than the scale of one of them.
What is this small lambda in the beginning of the expression? Lambda delta, lambda.
Just to control the order of the perturbation expansion.
Okay, so you're perturbing in the initial.
Yeah, in the initial potential and the initial stochastic contributions that I'm supposing that I can also expand as well.
So kappa is the kernel.
Kappa kappa is given by the dynamics of the system, right?
So this is not a time evolution.
Which is, I am supposing here that it's inside K here, right? It's not initial, but you have the time evolution here.
So you are just parameterizing the perturbative solution to the equation.
Yes. But of course, I have some assumptions here, which you write down this explicit form here. That's not very important, okay? But it's still one that I'm going to use. But I can also assume that the operators are local configuration space. Okay, I don't have convolutions here. Right, only the usual convolution, but no the convolution that comes from non-local operators. For example, the non-local formation of tracers, for example, the non-local formation of halos, because halos are not points, they are like spheres, and they have a non-local formation history because they start really large and contract. So this non-local formation can be parameterized inside the data as well, because you can imagine that you can just take the non-local operators and expand in terms of local operators. So this supposition here of local operators not so bad.
So just for me to understand better, if you suppose you're doing just linear evolution. So in that case, what happens in this equation? So this kappa is going to draw
Linear in for what field? For both fields?
linear in delta, yeah.
But what order for epsilon? We have two expansions here, right? But let's suppose you are consider this case here. right?
Okay,
So
But basically, M is the number of derivatives, no?
and
M is the number of derivatives.
no, the number of epsilon fields.
And sorry, M.
Yeah, it's the order. Yes, like this. The maximum order that ends the PTM, and the zero M is the order of this particular term of the summation.
so I guess linear just means that n equals one.
Yeah, it means this the usual linear
Yeah,
means something like this.
okay.
This
It should be just the growth function, right?
not so simple, right? Because you have B1, you might have all other stuff here. This is the usual linear approximation.
Just because I have a stochastic term.
Yes, we always have this stochastic term, right? Because you have the effect of small scales on large scales.
But if you're at the linear level, yeah,
Yes.
even at the linear level,
Yeah. Always that you try to write, for example, the power spectrum galaxy, you have to write something like this, right? Something like this.
yes,
This is the smallest scale effect on large scale, right?
yes,
It is linear level.
yes.
Actually, you could even just put galaxy not following the dense field, you would still have this guy. So the epsilon sometimes is more important than delta. That's why I have two expansions here that you have to make a choice. What order you want to stop.
So that's short noise.
Yeah.
And then, but the first term, the k, what is the relation between k and the linear growth function? It's the same.
Arrow function. Yeah, we put
K10.
Yeah, k10 is the linear growth function
could be anything here, right?
at the linear
An
level.
example could be B1, could be everything multiplied by the
Oh,
linear
let's say
growth
it's just
factor.
matter. Let's say it's just matter, no galaxies.
Just matter.
Yeah.
You could have a contra term here, right? This comes from EFT. Something like this would be the usual for just matter. So the growth function,
The first term is the growth function. Then you
Yeah.
have a correction.
yes.
That's one plus this case variable.
Yeah, just the usual matter term, right?
Then
But usually more general case, you could have B1 here that describes how is the connection between the tracer and the matter field. You could have the effect of primordial non-Gaussianities in the formation of the tracer. You could have a term like this that accounts for the EFT contra terms, but also this is the kind of term that comes from the expansion of the non-local operators in terms of the local ones. Okay, and we'll have many other things here that doesn't matter if they are linear in delta here. It's just a constant. Would be as complicated as you want. And the same thing for the stochastic field bars. Okay, just a generic model. That's not the most generic one, but it's more generic than many other models that we usually use.
And then if you go to nonlinear, this k will have this kernels of perturbation theory. Usual kernels of
Not just the kernels from perturbation. You could have a size, for example, K2. Now they have two wave numbers here. This is the guy that comes from that will multiply delta square. And this guy could be F2, which is the guy that comes from the perturbation theory for the evolution of matter from GR. Could also have a P2 here, which is the second term that describes the connection between the tracer and the matter. okay, which we are also expanding. You could have similarly something like BG2, which is the Galilean term, the Galilean operator of second order, with its respective kernel here. Could have corrections because of PNG, so terms that goes with the fourth, and so on. And of course, also terms that comes from the normal operators. There's many things here. But the whole point that doesn't matter for the computations of the likelihood. Because for the likelihood, the idea is to integrate over delta and not over the parameters here. And you see that all parameters of the model are inside the kernels here. These fields here have no information about the parameters. Okay,
So,
this is very important.
so just to understand, this is an expansion of delta in terms of like spectrum, free spectrum, and so on. Like to the somebody a little bit more.
No, it's an expansion at the field level, right? It's an expansion of the field delta in terms of two fields here. Just delta for the matter or the primordial potential, right? And something that is not correlated to delta.
Yeah, but this is so generic that it could apply to anything, doesn't need to be the density contrast.
Yes, that's the point. Could be anything here. Yeah. Here, just the point that to be able to compute something, both fields here should be something close to Gaussian. But Gaussian is the usual the solution of the index. Yes.
The small n index is it corresponds to a term which is like the linear term in delta or the quadratic term
In delta, yes.
in delta. So like it's an expansion. It's higher with the powers of the power spectrum, whatever. Like 2-point function plus the 3-point function that.
Yeah, so far there's no information about the endpoint functions here. The information about the endpoint functions here in the prior,
No.
which is the next point. But here it is completely agnostic to the endpoint function of both fields here, or to the PDF of both fields here. Okay. It's just the almost the usual standard perturbation theory in cosmology. It's just a bit more. It's not okay because the usual expansion, just to remember you, is something like this, right? Where we expand the anything here actually, and pointed out in terms of the operators, the bias coefficients, and stochastic fields one for each operator. Right? This is the usual, the standard perturbation theory, standard expansion. The only difference here is that I am also expanding this guy in terms of other operators that are not constructed in terms of the original potential, but in terms of other things.
Let's rephrase the question. So at the end, then, give us a spoiler. Would you want to replace those products of data as 2-3-point function, or would you leave it as that?
No, you got that. Okay. Because I'm going to integrate over.
Okay.
One knows how to.
Yeah.
Yes.
Yes. Then the last one.
Thank you. So, okay, so the idea is to use some theoretical expression. Now you have to give some prior for your fields here, right? Delta and epsilon.
Sorry, before you continue, the only stochastic variables are the epsilons.
Yes.
So why the initial conditions are not stochastic as well? They're realization of some values, because they come from inflation, they can
Yeah.
be stochastic as well, but they're.
This is the solution of inflation. Right?
So but the only prior of delta,
Delta and epsilon.
And apps.
Yeah.
Q, so what is Q? The capital Q,
Is the
covariance of,
the covariance of the absolute fluid, the cross and auto force factor.
which which handle you have to move that? Do you know it? How do you fix it? Do you think you know?
So it's a preferred. The same thing of P of K, right?
Okay,
We don't fix P of K. You have some model for the general shape P of K and function of the parameters. Then the whole point here is to actually fix K. That's the goal.
okay, you show it with that.
Yeah. So,
So this delta is the final delta, right?
yeah,
Prior to the final delta.
which one?
The prior distribution,
Yeah.
the first delta, no, yeah, this delta.
Yeah.
Which delta is that? That's the final delta.
No, the same one.
They say that Q wants.
Oh, so delta is also, okay, so delta is also,
Delta is the primordial
also
gravitational
stochastic
potential.
variable. It's also a stochastic variable.
Yes.
Okay.
Everything's. Sorry, but delta and epsilon.
Delta and epsilon are stochastic variables. Okay.
Yes.
So, Rodrigo, so you're saying that the prior comes from the initial condition, right, from inflation, right?
Yes.
So if you have remote uncertainty, that implies that the prior will change.
Yes.
And then, okay, so your configuration allows you to change the prior and also the modeling then.
Yes, of course, perform the computation is much harder if the
Right.
prior is not Gaussian,
Yes.
but you could, if you know the PDF for your initial
Right.
condition, you could, you should try to use persuasion here to compute.
Right, so you can have, for example, more general PDFs for the prior.
Yes.
And then have them in.
Yes. So, okay, once I have the model, I have the prior, the likelihood is fixed, right? It's just so the probability function of finding some set of observations given delta, given epsilon, and given the parameters, just given by product of hierarchy functions here, right? Because we are, of course, assuming that our model is reliable, which is always the assumption in cosmology. Okay. Let's remember that the first likelihood was something like this, right? Determinant of the covariance here is not limits. Okay. Here we had observation minus theory square over the covariance. Like this is the usual likelihood that we usually use. Simply right, so this is the usual likelihood that we assume. A GX function, which is not the case, but we are implicitly assuming some prior for this noise field or stochastic part. Because again, gravitational is deterministic, right? We must have something like this there. There is no way around. So, for example, if you take the usual likelihood for the power spectrum, the simplest thing here, just something like this, right? With the normalization here. You are basically assuming here that you're assuming something like this for the distribution of your stochastic part of the power spectrum. So you're basically assuming that your Yeah, the power spectrum of the stochastic field is Gaussian, which means that the distribution of the stochastic field is not Gaussian, something very complicated that I have no idea what it is. And you also assume some very specific covariance for the stochastic power spectrum, which is a really strong constraint. Okay, and that's important. It's really strong, and it's not flexible at all because you are fixing this guy here.
So capital T in this expression is the number of observations you have.
Number of tracers, because it's general in case you have multiple tracers, right? You could have not just galaxies, but you could have blue galaxies, red galaxies, halos, gravitational waves, shapes, many things. So you would have many tracers. So then,
So if you have just one tracer, that expression below, once you move, for example, like it's the product of the K-modes. So basically in real space would be direct delta between your observed power spectrum and the predicted one. Like it would be the difference between the observed minus the predicted spectrum.
did you understand your question?
Like
What was the question?
that product in K basically is an integral of K. In real space will look like just for just one trace it would be like the
Sorry, the product of K is not an integral, right?
yeah, because you
The integral is a summation. This is another thing.
yeah, sorry, I'm thinking in the Gaussian way, like when you have a product of many Gaussians, it becomes just the sum of
Okay.
okay, good. No, sorry, I think. Yes, so my question is at the final, like if everything is Gaussian and the likelihood is Gaussian, you have just one tracer. That's just the difference between the observed delta minus the predicted one. The year likelihood.
So it's always the difference between the observed delta and the theoretical one.
Yeah.
It's always, this is valid for anything. This is not subjected to the assumptions here. This is completely general, right? Because again, gravitation is deterministic.
Yeah, sorry, is that for me is a very new way of writing.
Okay, sorry. Sorry.
I just trying to understand like
Okay.
what is this definition of what like for a simple case it would be like how do I interpret this as chi-squared in the most simple expression?
If your theory is different of your observation, it's zero. If it's equal, it's finite, but would imagine that's fine. So it's just something that is, you cannot define a chi-square. It's something like this, right? It's a G-Rex function. So yeah. Just become this G-Rex delta function becomes wider because of the prior. Right? If you try to marginalize over the stochastic field or over the density field. In this case, you get something different.
So in this sense, it's still level because there is no space for having a stochastic distribution of the density field. It's just the observed density field, and the likelihood is one if it's the observed 1, 0.
Yes.
Okay. Yeah.
Yes, this is all information that you can capture from your observation, right? Your field. It's not just some summary statistics, it's the whole field. So, okay, let me talk about the results now. So
you can make it in half an hour. Yeah, half an hour. Can you?
yeah. Really quick. So the idea is to, as usual, to apply the theorem. So we want to compute the PDF of theta given the data. So we only have to compute something like, sorry. So in that way, we only have to marginalize over the initial fields or our PDF. Times the prior here. So from the expressions here, you only have to compute this functional integral here to find the likelihood. And yeah, this we can do, right? Because you have here the Gaussian in the prior. So you have like this, the free action here, right? And here you have the interactions. So it's basically the same computations of quantum field theory. It's very similar. We can just use the same tools. So for example, at first order, which is this case here, you get this final likelihood here. So let me talk more about this likelihood and why you have everything here. The first thing that you can see is the dependence in the observed basic field. And the only dependence is here, inside this integral here. So from here, you can see that the only thing that you need is actually the power spectrum. Because this guy here is a numerical estimator for the power spectrum, right? Because I have something like this, right? This is a continuous sum, which is not an integral, but it's a continuous sum. Here I have another thing before talking about the observational part, you have the theoretical part here. You have this term here, this contraction here. It's just the analytical expression of the three-level power spectrum. Don't know if it's clear from this expression here, but this matrix C here, in case you don't have any stochastic field, something like this, distinguish something like this, right? Zero here, it's the linear power spectrum. So you get for free what is the contractions of the kernels and the covariance of the initial conditions that you need to include in your likelihood, which is just the theoretical conditions. You also get for free what is the summary statistics that you have to use to have all information in the field. Okay, so it is not a field level likelihood, but it is a likelihood with all information in the field. Because again, this guy here, I can break in small beams where the power spectrum is more or less constant. So this just becomes like this, right? Where Ni is just the number of modes. So you see that you get for free the power spectrum here. Yeah, I think that's basically the main result is this idea that first of all, you can compute the likelihood analytically if you have perturbation theory that you have, because you need the perturbation theory to compute the prediction for the power spectrum and the bias spectrum anyway, right? So just with a little bit more computations, you get everything here. You get the summary statistics that you have to use. You don't have to choose. You don't have to think. If you are going to use the power spectrum, the bias spectrum, some combination, you don't have to think. You know which one you have to use. You know what is the theoretical prediction for this guy. Simply this contraction of the kernels here and the covariance. Also, same thing here in the normalization. You of course get all the analytical expression for the likelihood. You don't have to use any central limit theorem or any other approximation. You don't have to compute the covariance because, of course, you have everything here, not just the covariance, but all moments of this distribution, which are not zero after the covariance. Okay, so basically you have everything in this way. just starting from the same assumption, basically, and performing some more computation. So when you go, this one interesting point here is that this computation, we have to assume a first order perturbative expansion in the beginning, but all other computations we can compute full without any expansion. So you get this term here that it's, to pay attention, you see that this term is actually non-perturbative in terms of the kernels here. This is a term that is something like this, right? Exponential of minus 1 over x, which is a tunneling term, right? But for the linear kernels, the kernels of the linear terms here. So you have a term that you cannot expand. In fact, the expansion of this term is 0 at any order.
So yeah, I'm a bit confused by this very good question. Why is this like an unlikely looking Gaussian if we did not assume that in the very beginning of the selection? It's because of the variable, because we use like Gaussian variable.
Yes, it's looking Gaussian for the field, right? But for the power spectrum, it's not Gaussian. Right? Because it is just something like this. Exponential of, it's linear in the observational power spectrum. It's not quadratic in the exponential. So it's not Gaussian for the power spectrum, which makes sense, right? Because the field is Gaussian. If the field is Gaussian, the field square cannot be Gaussian.
We know that the field is Gaussian from the prior, because
Yes.
the observed field can be whatever, right?
Yes, not just from the prior, but also from the order that we truncated.
Okay, you just said quadratic order, your only option is to have a Gaussian.
Yes.
Okay. Yeah.
But yeah, this is important that this final likelihood is not Gaussian in the power spectrum. Okay. It looks very different from the Gaussian likelihood, but in fact, the Fisher information is the same, and the results are the same, are more or less the same of the ones to just assume a Gaussian likelihood. The details here are not very important, but the columns are just different parameters. You have AS, omega CDM, Lero 8, and the amplitude of the amplitude of the power spectrum of the stochastic field. And the x-axis is just the size of the box. So for smaller boxes, we expect that the central limit theorem is not so strong. But yeah, even this regime, both likelihoods give the same result. So the likelihoods things very different, but gets basically the same information of the Gaussian one. But at least this is consistent. And if you go to second order, now you have to really do perturbation theory to compute the likelihood, but you get everything that you want. For example, here in this term here, it's not very simple to identify, but this guy here is just the observational bispectral. You see that you have some combination of the real here and imaginary parts of the observed density field, but it's just the real, this guy is just the real part, delta 1, 2, 3, 1, 2. So we get the conservational point here, right? So the triangle is closed. You get the real part, which is good because the nature is real. So again, for free, you get the bispectrum here. So at second order, you only need the power spectrum that is inside the 0th order here, and the bispectrum. Here, you see this in the denominator, you have the product of 3 power spectra, is just the covariance of the bispectrum at the leading order. Here, you have just the theoretical bispectrum at 3 level. You have basically 2 first order kernels and 1 second order kernel, which is some limit will be this guy here. which is the three-level prediction of the bispectrum. You also have this extra term here that have the first one-loop correction to the power spectrum. You see here that you have two second-order carriers inside the integral here. Summation that is, you can imagine as an integral. So again, you get all the terms that you are expecting, and now the functional form is really different, right? But because we use the perturbation theory here. But it's, you can also see that all terms here are of the type theoretical prediction times observational quantity divided by the covariance. It's something like observational times theory divided by covariance, which is the linear term that you get from this, right? In terms of the theory. Which is basically, you could imagine that is the, if you expand the exponential, you'll get something like this. And again, you have all the covariance for free, or the covariance for the bispectrum for free, the covariance for the one-loop correction of the power spectrum for free, which is just the pre-level, this order. We have the cross covariance for free. We have basically everything for free. And you can do the same thing, but
Sorry, but this is the probability distribution for before is the likelihood for delta zero given the parameters.
yes.
Not for the, but then you get contributions from the power spectrum, the bispectrum, etc. For this quantity, which is at the field level, given likelihood for the 2-point function, 3-point function, what do you have to do?
I don't know. You would have to, we start here, have a prediction for your endpoint function, and be able to have some prior for your endpoint function, or at least for the thing that you are using for your endpoint function, to do the primordial thing here that you are using, the primordial field or primordial structure that you are using, which for the power spectrum is not very easy. Like,
So it's not trivial.
yeah,
like
because the problem is the prior, right? What's the prior of course?
It's certainly non-Gaussian, right?
Yeah, I would say it's probably this guy here, right? You'll get something like this if you try to compute. So this guy would be your prior for the power spectrum. You have to use something like this and try to perform the integrals, but yeah, not sure if it's really possible with this gamma function here.
So in principle, this is useful for field level analysis.
Yes, yeah. The idea is that why I want to use for endpoint functions, like why I want endpoint functions. There's no good reason, right? The only good reason because field is hard.
They're easier to measure.
Yes, okay, but yeah, I understand. But you see here that we do for field, but you see that you only need the endpoint function, right? We still don't have to really measure the field. You only have to measure some contractions of the field. And here you can see what are the contractions. You have to measure this contraction if you want to stop at first order, which is the power spectrum. If you want to go to second order, you have to measure this contraction as well, which is the bispectral.
But again, the likelihood is for the field.
Yes.
So that's observable. That delta O is the observable, right?
Yes, but
So we're measuring the field.
but again, the field only enters in the likelihood through these specific contractions.
Have to measure to compare with the data, right?
No, you can just measure the specific contractions. The likelihood doesn't care about the rest, right? The likelihood only cares about the specific contractions that you have here and here. So you can still only measure the endpoint functions, but now you know that you have all information.
Right.
And you know how to compare this information with the theory. which is this way. This is correct. It's not a guess from the central limit theorem. Yeah?
Where is the Q matrix? So the covariance of the epsilon parameters. Actually, like in the slide in prior, the covariance for the epsilon.
Okay, yeah, sorry. I assume it's just one tracer. So this matrix here is just a number now, just Q. And you have this guy inside C here. Yeah, this I took from the paper, but this matrix is just combination of the initial power spectrum for delta and for epsilon, if you have just one tracer.
One tracer. Sorry, I'm not from the field.
Okay, yeah.
Is it matrix or is it various epsilons or only one epsilon?
It's just one epsilon.
Ah, okay. So
Because-
it's just one motion to the other.
Yeah, because the idea is that the primordial gravitational potential, you have only one always, right? But if you have many different observations with many different types of tracers or objects, you might have different stochastic fields, because the stochastic fields comes from the UV completion of the modeling, and the UV completion is different for each field. It's the same for the kernels, right? It has the dynamics of the fields.
So in this case, Q would be just the short notes, right? 1 million.
Could be any function actually.
Like for one tracer, if I'm just measuring number of galaxies, would be the bias.
Yeah.
The short note.
Yes, because in the power spectrum analysis, this guy is usually something like this, right? It's the usual parameterization that people use. So yeah, it would be something like this.
Yeah, a linear level, let's see, would be the Gauss bias, and one would end the short notes.
Yes. Yes, this guy here is actually this contraction of K1, C K1, can write as under the simplest approximation, yeah. So it's just the theoretical prediction, but here it's with any can, it's just the most general way to write, yeah. But yes.
So just come back to my question.
Yeah.
So if you have various epsilons, did you do the computation with various epsilons?
Not for this. I did, but not in the paper. I don't have the results here.
It's trickier, but it's a nice computation. So.
Yeah, it's not much trickier, because the only difference here is that instead of two fields, I will have n fields, but the integral is still a Gaussian integral. The only difference is that the Gaussian integral in a higher dimension.
Yeah, right. Just yeah, okay, maybe it's.
And just to comment, you can also not integrate over delta and epsilon, and just over epsilon, and get the field level likelihoods. I don't know if you guys are familiar, but some people are trying to do cosmology using the whole field. So I'm trying to really find the initial conditions of the universe at the same time, together with the cosmological parameters. And you can also compute this likelihood. There is no problem. The only difference now is that we remove this integral here, and now this becomes a function of delta as well. So at linear order, you get this. This is just the EFT likelihood of the same result here. But we can also go to higher orders. Here, for example, is including the first term, the term, the kernel with 1, which includes this operator here, delta times epsilon, right? The first operator that correlates both fields that are uncorrelated in the initial conditions. So yeah, you get something this shape. Doesn't matter too much here, but you also have some kind of bispectral expected. So yeah, I think like this, yeah, this finished the part of the theoretical way of computing the likelihoods. So the whole point is that if you compute this way, you have a consistent likelihood. You don't need to compute covariance, super boring. You don't have to compute you have to compute, of course, the theory, but it comes from the likelihood. And yeah, you have basically everything that you need here. And you know the survey statistics that you need to actually measure from the field. Yeah, you have everything. It's not much more complicated than the usual, but the complicated. The only difference now is that you have to perform something, but just Gaussian perturbation theory is really similar to quantum field theory. You can basically write down some kind of partition function and compute the derivatives to get the higher order terms and so on. Not very complicated. So now a completely different way of doing it. Now suppose that I have no idea about the theory of my observable, but somehow I know how to simulate this observable. For example, I want to measure the power spectrum of blue galaxies in the universe. I have no idea how to compute it, but I know that I can put a lot of particles in a box. I know that the gravity is Newton, and I just evolve this box with particles in time, and I know how to, from the particles go to the blue galaxies. So I have a prediction for the power spectrum of the blue galaxies, right? So the idea is that once you have this kind of simulator, you actually have the likelihood as well of your data, right? Because your simulator is just something that you put a bunch of parameters, let run for some time and get your observation. And you can put your same set of parameters, and you are going to get another observation, right? So your simulator is your likelihood, but it's of course an implicit likelihood. You don't know the functional change of your likelihood, but it's inside your simulator somehow. So the idea here is methods is to try to use neural networks to interpolate this implicit likelihood. So the procedure is the following. You choose some set of parameters that comes from your prior. Okay, you must have some prior of your parameters. Then you put your set of parameters in your simulator and get some observation. And you do it many times and can construct this pair of parameters and observables, or parameters and data. And with this pair, you can use generative models to find this likelihood. So the most direct one is, for example, normalized flows that I talked about the last time. But there is actually really simple. The idea is to actually find a map that goes from some initial variables to your data, right? Let's say this is a map F. And if you have this kind of maps, you know from observational probability you can use it to find the PDF distribution of D. Okay. Distribution of the log here. Just I have to use this expression. This is the expression of the normalizing flows that comes from observation probability. So now you have the pair, you generate a lot of this, pairs, so you have this set. So with this set, you try to use neural networks to parameterize this function f, and using the inverse of this function f, try to go from your data to z in such a way that the distribution of z is, for example, Gaussian. Not sure if it's clear, please. I have any doubts here. But yeah, but it's super simple, but at the same time it's super powerful, because you can, first of all, you can resample from this likelihood supershift, because the idea is that a supershift to sample from this guy here, which is usually Gaussian. And then once you sample from the Gaussian, you just have to apply it in your neural network and go to your data. Okay. So of course, if you want to compute a likelihood or something conditional, everything here becomes conditional. So all functions here becomes conditional to theta. Change that in the computations. This is super quick. The last talk was just about this slide, I think. So I don't go deeper here, because of course the problem here are the technical points. How to make it to work with really high dimensions, how to train this stuff, what kind of neural architectures of the neural networks you have to use. For example, here one thing that's very important here, that in theory you get for free, is are the symmetries of the problem. So if you are trying to do something, for example, field level 2 or 3D, you have not the problem, but you have the thing, the symmetry, right? SO3 or SO2, and you have to be sure that your results are invariant to this symmetry rule, and it's not trivial to implement in a neural network. Yeah. Yeah, just a summary. The first point that it's very important is that there is no point in computing theoretical prediction or constructing emulators or observables or covariance of the observers or anything like this, right? Because if you can analytically, theoretically, or analytically compute these guys here, you can just compute the likelihood. And if you need to construct emulators, it's because you have a simulator, and if you have a simulator, you can just extract the likelihood from the simulator. You are basically, when you do something like this, you are basically trying to work around, right? Because you want to theta, you go to data, so you are basically trying to learn how to go to some summary statistics and how to go from summary statistics to here, right? My whole point is that you don't need this like first steps. This is well defined, and then it's easy to compute stuff. Yeah, it's very important to notice that the usual way of doing inference is formally inconsistent, because we usually assume, for example, that the likelihood of the power spectrum is Gaussian. At the same time, the likelihood of the pi spectrum is Gaussian, which of course makes no sense, because the power spectrum is the field squared, the pi spectrum is field cubed. The field cannot be Gaussian in both bars, right? And yeah, it's just what I just said. So yeah, that's it.
So the standard approach can be too wrong. If you try to quantify the difference, that's a difficult example.
Yeah, I tried here.
Okay.
You have no difference. But this is just the Gaussian case. You have the power spectrum here. Okay. I'm not sure about when you put the bispectrum or higher resolutions. You of course have to. Yeah, because Here in the case of cosmology, you have the fact that you have a lot of moments, right? And so the Gaussian mean, the moments of the distribution goes inversely with the number of modes of your substances. So they are maybe two types. But the point is that both computations are as extensive. That's why I should use some approximations to just use the correct expressions for free.
For equal amount of sweat.
And another point that's important here, that for example, suppose that you consider a core spectrum at 7 loop order, and a covariance at first order, one loop order. You, of course, you have some problems. You're gonna have some problem in the K-max that you can use just because of this inconsistency, right? Because if you have a very good prediction, but your covariance is not good, you probably have to stop at a lower value of K max, and just because of this inconsistency, because you are basically imposed some constraints in things that you are not pay attention to. So that's important to also have control over the range of validity of your knowledge.
So this is published.
Almost, yeah.
So no.
Yes.
Oh, okay. So it's just a curiosity, but it's motivated by something you said. Like you said that Galaxy formation is very non-local, and then when you wrote the endpoint function, then you do like the EFT expansion. That's fine. Do you know if people do like non-local things, like use a non-local operator, or do everyone always expand?
I think that always expands because the scale of the formation of the tracer that you are looking at is much smaller than the scales between the separation of the traces. So pretty much the extension is fine.
Yeah, I believe it's fine. I just was curious to know if you
Yeah, I
have
think
like
that-
non-local action. But
Yeah, the people use this non-local actions when talking about, for example, gravity. Then there are some papers that try to use non-local gravity, things like that. But talking about the formation of galaxies, then it's
okay, enough.
only local operators.
Yeah, it's not like two comments. One about this not necessity of going from data to summarize statistics. I still think that there is some, value in it. For example, BAO are unobservable, which is defined from the summary statistics and flexibility. So field level, when you get the BAO, when we go to the start in this approach, but I will not be able to think of the brighter likelihood of a BAO feature at field level. At least I can only identify it as, widgets.
Oh, it's here, right? This is the PAO likelihood. You have it here. You can just have to replace this guy here. Now theta is only your BAO scale, right? Because where's the linear? But you can always write your linear as something like some amplitude here that's not dependent of any parameter times some sine function, right? This is the, and here you have your theta, which is related to BAO, right? You can write something like this. This is the usual way of doing BAO, right? Because to do BAO, you have to remember to have to measure the two-point functions anyway, right? So it's even worse than this. You are actually doing something like this. Then try to go from here. But
I mean,
you can do that, right? But
if one, I cannot see how to go from D to BAO or theta BAO, like just from the field level D, because it's a very specific measurement. You have only the data. Instead, it's very clear if you have the prospect, the observer prospect.
I didn't understand.
Together.
The points that here you also have this integral here, right? This summation, that if you have some scales here that are not important, that are not affected by your theta, they are just an overall constant. So you can imagine here that you don't have to sum over all case, but only over the case of BAO, or if you have some other feature, suppose that you have a BAO in Fourier space, something like this, you would have to sum over only one over 1K, then this would be directly the likelihood. But for the case of BAO, if you write something like this, the usual one, you could perform this probably this integral over K analytically and get directly something for just for the BAO. But yeah,
I mean, well, if you want that expression there for the video accounts from the fact that we know the statistics of the video. We know the voice pattern, so we know that we parameterize the video feature that way, but
yeah, but
like
you can do that, but the point is that you are not getting all information, right? Because you are basically neglecting some part here. But that's fine. You can take some parts of this likelihood here and say, okay, I don't want to get all the information that I can get. I can only get some part of the information that I have interest. So you can just again perform this integral over K here, and the part that you don't care, it becomes just a overall normalization that doesn't matter for your MCMC.
my second question was about observer dependent biases. Like, is there a way to understand how I can implement stuff like, in those are not that technically stochastic variables, right? Like Marquis bias, or the fact that we live in a overdense or underdense region. Like, is there a way to implement that in this formalism? Because, like, for example, those effects have a very easy. You can predict the impact of Marquis bias on supernova, but you are building some statistics because you will actually compute that effect on the whole diagram directly, not on the field level supernova. So I'm wondering if there is a way of doing this type of analysis with these formulas.
I suppose that if
Basically, if epsilon is not a stochastic part, like because it has an observer dependent quality inside.
I think that if you have a good modeling of these observational uncertainties, you could just put here in a similar, probably you could put here in the end, but you also would have to know how the observational uncertainties affect your initial, not initial, but maybe your final observable. Because, for example, here you could start from something like this, get something like this, then you say, oh, here I have the power spectrum, and I know how the observational uncertainties affect the power spectrum, but not the field, right? So you could try to include here. Then you say, oh, okay, now I replace the smooth prediction by something with this noise, I don't know, and try to integrate it out.
For example, let's suppose I want to wave traces which are very distant because I only see the one very bright rather than the faint. That will, in that case, it will become as a term that upgrades on the K values. It will be a K dependent correction of that K kernel.
This would just be a different selection of tracer, right? Or
Yeah, it is. So
you just have to change, basically change maybe the shapes of the kernels, maybe the initial power spectrum of the stochastic field or something like this. Because then here you have you also have here this lambda O is the observational cutoff scale. So the point that you are taking, but this region here could be any region of your data. It's not very important. So no, it's not answering your question, right? So sorry.
I think we have time later. And we can break for lunch now, and we recommend it too, but not before. Thank you, Rodrigo.
monopolize the discussion.
No, no problem. Thank you for the